Hello, everybody. I'm going to solve the question occurred in your boarding tutorial, question 3B in week 3. This is the course Maths 2601 at University of New South Wales, Higher Linear Algebra. This is related with basis of subspace of the space of the polynomials of degree smaller than or equal to n. Anyone interested in with the coordinate vectors, it will be a good exercise to look at it. Okay, what is the question? The question is, we have the space. This is our notation. We usually use this notation for the space of the polynomials of degree n smaller than or equal to n. That's a vector space. We fix, for this question, we fix an alpha, a real number, and we define a set consists of the all polynomials such that p alpha is equal to 0. It means that the all polynomials with the root alpha. It is easy to verify that V is a subspace of the vector space, but this is not our task for this question. In this question, we have set B. These are the powers of the linear factors, x minus alpha 1, x minus alpha square, and so on. And we would like to show that B is a basis for V. And we would like to find a coordinate vector of any polynomial in the subspace V with respect to the basis B. There we have two tasks to do. It is easy to see that for any polynomial in V, assume that we have a0, a1, x, an, x to the n. It's just any polynomial. And inside the subspace, by the definition of the subspace, alpha will be a root. Then p alpha is equal to 0. This, if you put this alpha in instead of the x here, we have equality. There's equality. But we can write a0, which is one of the coefficient, in terms of the others. So a0 will be minus a1 alpha, a2 alpha squared, and so on. So a0 is uniquely determined from a1, a2, an. So basically, V will be a dimension n because you have only n things to vary. And further, you can think of that x and x squared, x to the n will be the standard basis of this vector space. Now, B that we constructed here, that we given to us here, is a set of this kind of powers of the linear factors, x minus alpha squared, x minus alpha cube, and so on. And each of those ones have the different degrees, right? This one has degree I. This is I degree polynomial. This is a j degree polynomial. So the degrees are different. Since the degrees are different, B, the elements in the B, will be linearly independent. We can say this like that, or we can properly prove whatever you like. I also added the proof here. This is the proof for linearly dependency. But this sentences here is good enough. It is enough, you know. And if you want to prove that, you just take the linear combinations of those powers of the linear factors, make it equal to the zero polynomial. And zero polynomials is a polynomial gives you 0 for each x. And then you looked at the powers of coefficients of x to the n here, coefficients of x to the n minus 1 here, and compare the coefficients of x to the n minus 1 on the right-hand side. Since two polynomials are equal and all the coefficients here will be 0, then all the coefficients of the powers here will be 0 as well. So since x to the n is the largest one, if you look at the n power of x on the left-hand side here, you will have only lambda to the n, x to the n. You have only one coefficient, which is lambda n. And it is equal to the 0 on the right-hand side, so lambda n has to be 0. And if you look at the x to the n minus 1 power on the left-hand side, one of the power will come from the coefficient will be lambda n minus 1. All the others, all the other coefficient of x minus 1 will contain alpha n because it will come from here, right? You have x to the n, and then you have x to the n minus 1 appear in this one, but it has the coefficient of lambda n. But the lambda n is equal to 0, then this one will be 0. It implies that lambda n minus 1, 0. So this is what I'm trying to say here. By thinking of this way, you can go up to the lambda 1 is equal to 0 case, then you can prove that the lambda B is a linearly independent set. Okay, once we understand that the two important things that we have done up to now, we observe the fact that the dimension of V is equal to n, and the number of the elements of B is equal to n, and B is linearly independent. This means we have a theorem, we have a lemma. It says that if you have a set, a linearly independent set, such a number of the vectors in that set is equal to the dimension of the vector space, then it has to be the basis. You have enough vectors to span all. If they are linearly independent, it is the basis. So by using that theorem, B is a basis of V. We prove that part. Now we are going to, our aim is to find out the coordinate vector. What was the significance of the basis? Significance of the basis means that every vector, I've wrote it as a green here. If you have a basis, basis implies that every vector in your vector space can be written uniquely. Uniquely is an important part here, as a linear combinations of element of a basis. This means for each vector in your vector space, in this case, you have polynomial P and a vector space V. There exist unique, this means unique, this means there exist coefficients, lambda 1, lambda 2, lambda n. Then I can write this vector as a linear combinations of the basis element because these are the basis element. So this green fact, that's what I'm using here. Okay, then we would like to, this is a polynomial and we would like to find out lambda 1, lambda 2, lambda n. I'm going to use derivatives and I am going to take the derivative of this polynomial, first degree derivative, second degree derivative up to the n degree derivative, and by using the chain rule, and we will try to find out what the coefficients are. Okay, the first derivative will be derivation of this is just 1, so lambda 1. Derivation of this will be 2x minus alpha 2. I'm using the chain rule. So 2 goes down, x minus alpha, but the derivation of the inside with respect to x is just 1. So that will be 2 lambda 2x minus. You have the cube here, then you have lambda 3, 3x minus alpha squared. And the last one will be lambda n, and x minus alpha n minus 1, because the derivation of the inside with respect to x is 1. And now I'm going to take the second derivative of this. So I can move from here to here, taking the derivation of this polynomial here. This is a constant, will be 0, and this will be just 2 lambda 2. This will be 2 will go down, and this will be x minus alpha. In the end, I have alpha n and n minus 1, and that will go down one more, and it's n minus 2. Third derivative will be, this is constant, will be 0. And the derivation of this will be 3 factorial lambda 3. And the derivation of this is just 1. And then you have another factor here. I've wrote it here, but you may not need it. So I have lambda 4, and I will have 4 factorial. And that is a square term here. The square term derivation will be just x minus alpha. And the derivation of this part from here to here will be n, lambda n, n minus 1, n minus 2 goes down, and that will be minus 1. Now we can see the pattern. That's good enough to see all the pattern. And then the last one will be, all this will disappear, only this part will come. Then you will have lambda n, and all the way go down to the 1. And the last term is the nth derivative. So this is the third derivative. We go down 3. So this is the nth derivative. That should be n minus n. So this will be 0, or anything 0th power is just 1. So this is 1. Now, if we put x is equal to alpha in these values, we will have this 1 0, this 1 0, and we will be able to figure out what are the lambda 1, lambda 2, lambda 3, and lambda n. So that's what I'm doing in here. From here to here, I'm just evaluating at x is equal to 0. If we put x is equal to alpha, all this 0, then I have lambda 1. So lambda 1 will be just the first derivation. If we put alpha here, x is equal to alpha, then all will gone. Then I will have 2 factorial lambda 2. 2 factorial is basically 2. I just would like to write it down as a pattern. So lambda 1 is the first derivative. Lambda 2 will be 1 over 2 factorial, and the second derivative evaluated at alpha. Third one, so all will be gone. You will have 3 factorial lambda 3, 3 factorial lambda 3. So lambda 3 will be 1 over 3 factorial, and the third derivation of the polynomial evaluating at x is equal to alpha. Keep going, and just one before the last one, p to the n minus 1 derivation will be n minus 1 factorial, n minus 1. So, and that will be the n minus 1 derivation. And the last one is just the, will be just 1 because it's the last derivation. So this is up to here there's a pattern, but the last one will be just 1 over n factorial. So this will be lambda 1, lambda 2, lambda 3, lambda n. So these are the coefficients. So this vector here is the coordinate vector with respect to the basis b. So that's our calculation. Hopefully it's helpful for you all. Thank you very much for watching it. Thank you. Cheers.